Hello everyone, today I'm going to explain the main ideas of our magnetism model. I will keep it focused on what you need to show that you understand the topic. So, magnetic poles and dipoles. What the magnetic field P is and how we define the direction and how magnetic fields create forces. First on moving charges and then on current carrying wires. To start, magnetic poles have two distinct poles, which we commonly call the north pole and the south pole. Uh, the key interaction rule is simple: like poles repel and unlike poles attract. This means north repels north and south repels south, but north is attracted by south. When we have two opposite magnetic poles together, that forms a magnetic dipole. And an important point of the slides is that all know magnets are dipoles or can be modeled as dipoles or higher order combinations. Um, People theorize that magnetic monopoles exist. It's a magnet with only north or only south, but they have not been observed in our normal experience, experiments and measurements. Next is the idea of the magnetic field, represented by the letter B. A magnetic field is a way to describe the influence of magnetism in space. The slides define the direction of the magnetic field in a very practical way. The direction of P is at any location, it's the direction that the north pole of a compass will be if place it there. So, in sense, the compass is our field direction detector. We often represent the magnetic fields using magnetic field lines. These lines show both the direction and the relative strength. The direction is shown by narrows, the strength shown by density. The closer together the field lines are, the stronger the magnetic field in that region. Outside the bar, magnets fields are commonly drawn from north towards south, matching the idea that the compass north pole will be pushed to follow the directions. So now here's a major connection between electricity and magnetism. An electric current produces a magnetic field. This is one of the big ideas that set up everything we do later in physics too, including motors, electromagnets, and induction. In the slides, this is introduced by directly current wire creates a magnetic field around it. To deal with directions, we use right hand rules. The slides indicate clockwise and counterclockwise cases depending on whether we are talking about uh, positive charge or whether the field is into or out to the page. We use it a right hand rule to connect the directions of current or velocity, the magnetic field, and the resulting force of circulation direction. After we know what P is, the next step is understanding what P does, right? A magnetic field can exert a force on moving charge party. On moving, the field can exist on a moving charge particle. That moving patterns, if the particle is not moving, you don't get the same magnetic force behavior. The slide emphasizes that the magnitude of the magnetic force is proportional to the charge and the speed of the particles. To understand the relationship, it's F equals Q B sin of theta, where Q is the charge, B is the particle speed, B is the magnetic field magnitude, and theta is the angle between the velocity and the velocity vector and the magnetic field vector. The important relationship, the important interpretation in the angle part It's if the particle moves parallel to the magnetic field, which theta equals 0 degrees, sin of 0 equals 0, so F is 0. But if it moves perpendicular, the field where theta is 90 degrees, sin of 90 is equal 1, so the force is maximum. Another major concept is direction. When a particle moves at an angle to the field, the force is perpendicular to both velocity and the magnetic field. This is a huge difference from many forces we use to, because it means magnetic force often bends the part rather than simplifies bending the particle up or slowing it down. And again, the slides state directly that the right hand rule gives the direction of the force. Also, the slides give the SI unit of magnetic fields, the Tesla, written as a T. So if we see P equals 0.30 T, that means the magnetic field strength is in Teslas. Finally, we apply these ideas in circuits and real devices by taking about magnetic forces of current carrying wires. The slides explain that the magnetic force on a wire is basically the combined effect of the forces on the moving charges inside the wire and the practical equation we use for a string wire segment of L in the uniform magnetic fields. Which is F equals ILP sin theta, where I is the current amperes or amps, L is the length of the wire in meters, and B is the magnetic field in Teslas, and finally theta is the angle between the current direction and the field direction. To summarize the full model in a clean idea, magnets behave like dipoles with north and south poles. They create magnetic fields B, whose direction can be defined by a compass. With a compass, file lines visualize direction and strength. Electric current produces magnetic fields, and magnetic fields create forces on moving charge with F equals QVB as sin of theta, and the current carrying wires with F equals ILB sin of theta, with directions determined using right hand rules. There's the current standing needing to show you where's the magnetic constant for the model. So thank you so much. This is from the slide number 9 of our model in physics class. So thank you so much and have a good day.